Good evening. We'll continue from where we left off yesterday. We are looking at examples of rings. Consider the ring of Gaussian integers. Find the units of Z of I. The obvious units of Z of I are 1 minus 1, I and minus I. 1 inverse is 1, minus 1 inverse is minus 1, I inverse is minus I, and minus I inverse is I. So each of these four elements has an inverse inside of I. Are there any other elements that have a multiplicative inverse? Yes, yes. In complex numbers other than zero, all of them have inverses in simply the ring of complex numbers. But here we have constrained A and B to be integers. Then their inverse might not be of this form. They might not have integers. So, what do you think? Which other elements have inverses? Yes, that's so far good, but then here some manipulation is required. Um if you square this, what you will get? AC whole square plus BD whole square minus 2ABCD is 1 square equal to 1. And BC whole square plus AD whole square minus 2ABCD is 0 square, which is 0. Plus. And if you add them, you'll get AC A square C square plus B square D square plus B square C square plus A square D square is equal to 1. Then you can take a square common in the two terms. You'll get a square into first and last term, c square plus d square. In the middle terms, you can take b square common. You'll get b square into c square plus d square is equal to 1. Then you can write a square plus b square into c square plus d square is equal to 1. Now, a, b, c, d are integers. So their squares are also integers. And the sum of the two of them, a square plus b square is an integer, c square plus d square is an integer. So what two integers when you multiply you can get one? There are not many options, right? There is just what options are there? Yeah, but a square plus b square would be a positive number because it's a sum of squares. So it has to be one. This means that a square plus b square must be one. And sum of squares of two integers is one means what are the options? If a is any integer greater than 1, a square itself will be greater than 1. Uh, and the sum of a square plus b square will also be greater than 1. Similarly, if b itself is greater than 1 or less than minus 1, again its square will be greater than 1. So, to get this, there are just four possibilities. A is 0, b is equal to 1, or a is 1, b is 0, or a is 0, b is minus 1, a is minus 1, b is 0. Because we need integer solutions. So these four are the only solutions. But if you plug this in, if a is equal to 0, b is equal to 1, what is the number a plus ib? Yes. So these are simply 1 minus 1 I and minus I. So these are the only possibilities of a plus ib such that there exists a c plus id such that their product gives you 1. So these are the only elements that have an inverse. So the claim is that uh, 1 minus 1 I minus I are the only units of z of I. This would also mean that z of I is not a field. It is only a ring. Field is a ring in which all non-zero elements are units. We know z of I is a ring, but the units are only these four. There are other elements in z of I other than 1 minus 1 I minus I. So since those are not units, this means that it is not a field. Then one important ring is based on polynomials. A polynomial in X variable or simply symbol in X over R is a formal expression of the form a n x power n plus a n minus 1 x power n minus 1 plus etc. plus a1x plus a0. This is actually different from the polynomial functions, rational functions and polynomial functions in calculus that we see. There we assume that x takes some value and then you evaluate it. Of course, but here our definition has nothing to do with that. So equivalent way of writing this would simply be writing the coefficients. You could think of this as some vector. This would be equivalent. Huh? R is any ring. So any expression of this form, you have powers of x and you have a coefficient next to each power of x, and then you have some of these terms. Yes, I'll write that. I'll write that. Where n is a natural number, so you cannot have negative powers, and you cannot. These are all integers powers, and all these coefficients a n minus one, etc. They are members of this ring. These are called the coefficients of the polynomial. This is what a polynomial is. For example, if the ring is the set of integers, then 2x squared plus 5x plus 6 is a polynomial with coefficients from z. If r is a rational number, then we could have 3 by 2x power 100 minus 5 over 4x squared. So these are similar to the polynomials that you already see, but uh, generally in school level mathematics, the coefficients are from real numbers. But here the coefficients are from a particular ring, and you have to tell the specify the ring before. Then let f of x equals a n x power n plus a n minus 1 x power n, some polynomial in x over R. We say degree of f of x is the largest n such that an is not the zero element in the ring. And we use the notation R of x to denote the set of all polynomials in x over R. This R of x is an infinite set because it will contain x, x square, x cube, any finite n, it has x power n in it. and all polynomials of that degree in it. Yes. Z of x would simply mean polynomials in X with coefficients from the ring Z. You could specify R is equal to Z and then write R of X. Or if you have specific symbols like Z and Q, which mean a particular ring, which is if it's already understood, then you can directly write call it Z of X. Notation, it's up to you. For arbitrary rings, when we are dealing with arbitrary rings in some theorems, then we'll say for any ring R, consider the polynomial ring R of X. But if you are working with a specific ring, then of course it's better to use the particular ring or which you are talking about. Oh, huh? No, that is just notation that has been used for a long time. In textbooks, there will be bold symbols, that's all. But we can't write bold when you're writing down, right? So that's why you add extra R, you write like this, and C, you write like this, or like this. So this is just because you can't write bold letters on on the board or paper. Yeah, but convention in textbooks it will be bold letters. No, not really. You can simply say Q and R. From context, people should understand. Otherwise, if it is completely out of context, then you will have to say the set of integers said. Somewhere you have to mention before you use it. If it's in a paper, then once you can just state it in the beginning, some notations. Then this right now we have said R is a ring and we have defined a set of polynomials. But this is simply a set right now. But we want to give a ring structure to R of X itself. Not we have R is a ring. We want R of X also to be a ring. And for that we have to define addition and multiplication, which is simply the addition and multiplication of polynomials. Nothing new here. Only thing is that only addition and multiplication is the coefficients will involve the operations from the ring. So the ring has addition and multiplication, right? So whenever you have to add two coefficients or multiply two coefficients, there you use the multiplication and addition in the ring R. So we want to give ring structure to R of X, define addition. We add the like terms. That is, we add coefficients of equal degree monomials. It's, can understand better with an example. We have 10x power 5 minus 5x square. then the sum of f and g would be 7x power 6 plus here you have 10x power 5 minus 8x power 5. That sum would be 2x power 5. Now plus 5x square and minus 5x square, those will cancel out. Then you have 2x. Then you have plus 8 and minus 8, those will cancel out. So the sum is 7x power 6 plus 2x power 5 plus 2x. So what the difference is that here when you did this, for example, instead of that, if you had uh, the same thing, but the ring was Z8, okay, then f of x would have been 2x power 5 minus 5x square would be minus 5 is 3 in Z8 plus 3x square plus 2x and 8 would be 0. G of x would be 7x power 6 minus 8x power 5, that would go to 0. You would have 5x square and f of x plus g of x would have been 7x power 6 plus 2x power 5 plus you have 3 plus 5 x square plus 2x, but 3 plus 5 is 8, which is 0 in Z8. So when you add the coefficients, you are adding in the ring Z8 here. So this is 0x square, so you are left with this. That you could also get by simply taking this modulo 8. Is that clear? Similarly, with multiplication, we define we'll define x power I times x power j to be equal to x power I plus j and ax power I times bx power j to be ab, this is in the ring, x power I plus j. And same rules of polynomial multiplication. F of x is 2x square minus 3x plus 5 and g of x is 3x square minus 3. Then f of x times g of x is and this would simply be like normal multiplication 2x square into 3x square minus 3 plus minus 3x into 3x square minus 3 plus 5 into 3x square minus 3, which is 6x power 4 minus 6x square minus 9x cube plus 9x plus 15x square minus 50. Same way, if you had a different ring instead of Z, if you had Z8, then what would happen is this f of x would be 2x square minus 3x plus 5 and 2x square. Instead of minus 3x, it's plus 5x plus 5. Gfx would be 3x square plus 5. And their product f of x gx would be 2x square into 3x square plus 5, which is 2x square into 3x square is 6x power 4 plus 2x square into 5 is 10x square, which is 2x square mod 8. So you do 2 into 5, 10, which is 2 in Z8. Then you have 5x into 3x square plus 5, which is 15x cube, which is 7x cube, plus 25x, which is x, plus 5 into 315 is 7x square, plus 5 into 5 is 25, which is 1. You have 6x power 4 plus 7x cube plus 2x square plus 7x square is 9x square, is x square plus x plus 1. Of course, since this is earlier, it's the same thing. Earlier we had to set the coefficients were in Z. Here we took the coefficients to be in Z8. So instead of doing this, you could have also taken the final result here in Z8. That would be 6x power 4 minus 9 is actually O plus 7 in Z8. 9x is x and minus 6 is 2x squared. So that why is that different? Sorry, this is not minus 6x squared. This was minus 6 plus 15 was 9. So it was plus 9x squared. So this was plus 9x squared plus 9x minus 15. And that would be in Z8 x squared plus x minus 15 is 1. Yeah. Instead of Z8, if you have some other ring, then again, same as multiplication of polynomials that we have seen in real numbers, multiplication and addition. But when you're dealing with the coefficients, you have to do the operations from the ring from which the coefficients come from. We only need two operations for rings, right? So we consider only addition and multiplication. Because subtraction is not an associative operation and division is also not associative. Yeah, 2 by 3 divided by 5 is 2 by 15. But 2 divided by 3 by 5 is 10 by 3. They are not same. So that's why we don't consider subtraction. And if just from the group They fail group definitions also. Minus doesn't form a group. Yeah, and also we couldn't we did one problem. We couldn't get there's no identity for subtraction because a minus 0 is always a for any a, but 0 minus a is equal to minus a. It is not equal to a itself. So 0 is not the identity for, there's no identity element for subtraction. Which one? We just see subtraction as adding the additive inverse and division as multiplying by the multiplicative inverse. Later we will do division, but we will only use division for other purposes, but not as a binary operation because it doesn't have these associative properties. No. Yeah. We might define a division and use it to do some things with existing rings, but we won't use that as one of the main binary operations because division on integers it's not even close. 1 by 2 is not even an integer when 1 and 2 are integers, whereas 1 into 2 is an integer. So, but you could use the division kind of thing to write um, the GCD and all. That's actually from division only. Uh, we get uh, we use the division algorithm to write a is if you divide a by b, you can write a is equal to bq plus r, where r is between 0 and a. That is actually from the division process, long division that you do. So you might use that for other things, but you won't use it as one of your operations for the ring. Okay, once we have defined this addition and multiplication, uh, but we haven't checked whether it is a ring or not yet. So to check it is a ring, first we see this is obviously closed just from looking at the definition. The product and sum of two polynomials is always a polynomial in X with coefficients in the same ring. Then the additive identity is the zero polynomial. The zero element of R of X is the zero polynomial. And the additive inverse is if f of x is a n x power n, etc., a1x plus a0, then the inverse is minus a n x power n plus minus a n minus 1 x power n minus 1 plus minus a1x plus a0 minus a0, where minus a n is the additive inverse of a n in ring R. And since addition is commutative in R, uh, addition of two polynomials is also commutative. So R of x with addition is a abelian group. Multiplicative identity is the constant polynomial 1 You can easily verify commutativity and associativity. You can also verify addition and multiplicative distribution. So for we have that for any ring R of X with the addition and multiplication defined as before or as above is a ring. You won't really prove it, you just said it in words, said it informally. Once you have this, you can then see R can be identified as a subring of R of X, containing all the constant polynomials. No, there is no direct polynomial field. Yeah, you only have polynomial rings. Yes, yes. No, that's the reason. You can't get inverses that belong to the same polynomial ring. Yeah, because 1 over x is not a polynomial as such. It is a rational function. But we can construct like the rational functions. If we consider all rational functions instead of polynomials, then as long as with some minor uh, clarification in the details, that could be looked at as a field. And similar to how we did, how we took the equivalence classes, Z mod NZ, or it under the congruence modulo n relation, contained all the equivalence classes from 0 bar, 1 bar up to n minus 1 bar. Similar to that, we can say we can define congruency of two polynomials and the equivalence classes of polynomials of degree less than something. That way, we can get finite fields. We'll see that later if we have time. Now, like you said, we can actually divide. So division is useful in that sense. And but basically, whatever you do with integers, right, the same type of stuff you can do with polynomial rings also, because both are rings, right? Z is a ring and R of X is a ring. And the you have addition and multiplication in Z, you similarly you have addition and multiplication in R of X. So a lot of the results kind of carry over, not one to one, not exactly the same, but many things carry over to polynomials also. For example, we had the Euclidean division algorithm that you can apply to polynomials also. in R of x given two polynomials f comma g with f a monic polynomial. There exist unique polynomials q and r such that g can be written as q into f plus r. That is, you divide g by f. And we had, for integers, we had r is greater than equal to the r is greater than equal to 0 but less than the divisor. But here, there's no meaning for less than or greater than in a polynomial, right? There's no way to say some polynomial is less than another polynomial. But we can compare the degrees of the polynomials. We can say one polynomial has degree less than or equal to another polynomial. So this theorem will have that. You will have two polynomials q and r, unique polynomials, such that g is qf plus r, and either r is a zero polynomial, or if it's not the zero polynomial, degree of r is less than degree of f. And we say a polynomial, I said f has to be monic. We say a polynomial is monic if its leading coefficient is 1. The leading coefficient is the coefficient of the highest degree term. For example, f is 2x cubed plus 3x plus 1. This is not monic. G is x power 5 plus 6x plus 2 is monic. Because highest degree term is x power 5 and the coefficient is 1. If the coefficient 1 is 1, we usually don't write the coefficient. And you would carry out division in the same way as you do for integers, the long division. Uh, you multiply by 3x squared to get 3x power 4 plus 6x squared minus 3x squared. Then you subtract, you get minus 7x cubed. Sorry, this was 6x cubed. So this will become minus 13x cubed plus 7x squared. You bring down the 10x. Then minus 13x times x squared plus 2x minus 1 is minus 13x cubed minus 26x squared plus 13x You subtract and you'll get 33x square minus 3x. You can bring down the 2. Then 33 times x square plus 2x minus 1 is 33x square plus 66x minus 33. If you subtract, you're left with minus 69x plus 31. And degree of minus 69x plus 31 is less than the degree of divisor, x squared plus 2x minus 1. So you can stop. Now you can write 3x power 4 minus 7x cubed plus 4x squared plus 10x minus 2 is equal to the quotient 3x squared minus 13x plus 33 times the divisor x squared plus 2x minus 1 plus the remainder minus 69x plus 31, where the degree of remainder is less than the degree of the divisor. Only thing, if it's here the ring is the ring of integers, but if you had a different ring like the ring of integers modulo n, or the equivalence classes z mod and z, then all the operations you do have to be within those rings. If f is not monic, then the initial step might fail. Not always. Actually, f need not always be. If it is monic, then you can guaranteedly divide. But even if it is not monic, sometimes you can divide. But the thing is, the coefficient of f must be a unit. Otherwise, you can't divide. See, like I said earlier, division is not our goal. We only need division for other things. So whatever things we need to do, we will always have monic polynomials for that. Yeah. So it is a means to an end. The division itself is not very interesting to us. Sometimes in applications, you might be dealing with fields, in which case uh, you can you can always divide, because you can multiply by the inverse of the leading coefficient to get a one in the leading position. Yeah. So you might not be able to write z is equal to qf plus r, but you can multiply if f is not, if, for example, here, if you are dealing with coefficient, here it is not monic in zx. That is important. This is, I mean, it's not monic, but if it is in zx, there's nothing you can do about it. But if it was in q of x, say, then you could write, multiply the entire thing by half and write f by 2 was equal to some monic polynomial, 3 by 2x plus half. Then you could divide g by f by 2, and you could write g is q into f by 2 plus r, where degree of f by 2 is the same, is also degree of f only, right? So R is again some polynomial whose degree is less than degree of F. So you would just get an extra factor here. That's all. That is because 2 is a unit in rational numbers. The inverse is half. So if it's a unit, you can get around that way. If the leading coefficient is a unit, just multiply by the unit and do the division. And if you don't like this form at the end, you can simply multiply both sides. Okay. One important property is of this division. Let g of x be a polynomial in R of x for any ring R. Let alpha be an element of the ring. Then x minus alpha belongs to R of x. By x minus alpha, we mean x plus minus of alpha. That belongs to R of x. And this is monic. So we can divide g by x minus alpha. In all these places, you have to, even though I said this, let R be any ring, in everywhere we are excluding the zero ring. If zero is the only element, that's simply not interesting at all. So the smallest ring that we'll even consider is the binary ring containing 0 and 1. Okay, then if you divide the polynomial g of x by x minus alpha, the remainder is g of alpha. Can you prove this? Use the division algorithm that we. But degree of r of x less than degree of x minus alpha means what? Yeah. So 0 degree. So it is a constant polynomial. It's either 0 or some other constant in R. So R of x is a constant. Constant polynomial or simply constant. So what does that mean? Regardless of what value of x I give, my R of x will not change, right? When you divide by x minus alpha, uh, you get this equation. Then, regardless of what value you give to x, so one thing that certain thing here is that you can actually put values in place of x, can substitute them. Even though technically we are not dealing with a function, g of x is simply an expression in with x and coefficients from R. It is not really a function. It doesn't really mean that you have some x variable x that you are multiplying 5 times. That's not what it means. But similar to how a vector is just a list of numbers, right? But then you can consider a vector to be uh, pointing out a point in a Cartesian plane. So the vector xy, you could think of it as the point xy in the Cartesian plane. You can give it a meaning and work with that. But actually, a vector has nothing to do with points on the plane. Even if you had no concept of the Cartesian plane, you would still have the concept of a vector and a vector space. So similar to that, even if you had no concept of functions, you would still have this concept of polynomials, a polynomial ring. So that's why in the definition we say it is a formal expression in X with coefficients in R. So it's a formal expression of this form. That's all. It is one way of writing out the coefficients. It's a convenient way because it allows us to define these addition and multiplication operations, right? But actually, you could think of these as equivalently vectors an up to a0, and an addition is simply the addition of coefficients bn b0 if you have another vector. You simply add an plus bn. That's addition. And then multiplication, if you really go back and look into it, it would just be the convolution, convolution of sequences. Convolution is an a0 and bn b0. The first term would be a and bn. Then you would get an minus 1 b0 plus a something like that. This would be a0 b0. This would be a1 b0 plus a0 b1, so on. So it's actually a convolution of two sequences. This sequence an to a0 and this sequence bn to b0. So without writing it in this polynomial form, you could still define this as vectors and vector addition and the multiplication to be vector convolution, and you'd still get the same thing. So it's not that these things are actually functions, but similar to how we can use n-dimensional vectors to represent points in the n-dimensional space, we can consider these formal expressions as functions also. And we can plug in values for x. Okay, this difference is actually important because when you go to fields and finite fields, sometimes it becomes confusing. You can't differentiate between these things. From what point did you not hear? In a field, sometimes you evaluate a field, evaluate a polynomial, right? But the polynomial is from a different field. The coefficients of the polynomial are from a different field. But then when you evaluate it over points in a different field. For example, suppose you have a polynomial in z of x is x square plus 2, let's say. You could evaluate this at a real number also, right? You could say z of, suppose not z of x, f of x is x square plus 2, which belongs to z of x. You could say f of 3 by 2 is 3 by 2 whole square plus 2, 9 by 4 plus 2, which is 17 by 4. You could evaluate this way. But when you say x square plus 2 is a polynomial in z of x, it really has nothing to do with this type of evaluation. Yes, but we have modular arithmetic where z is a ring, but z mod pz for a prime is a field. You have that, right? Similarly, for the polynomial the polynomial ring is simply a ring, but polynomial ring modulo an irreducible polynomial would be a field. There also you would have equivalence classes. Then the equivalence classes, when you consider them as elements, they would form a field with multiplication and addition. But they are not actually polynomials. They are equivalence classes containing polynomials. Similar to how Z mod 3Z is not made up of numbers 0, 1, 2, 3 up to n minus 1. It is the equivalence class containing 0 and the equivalence class containing 1. See, the main doubt you are getting is because you can't differentiate between A mod n and A is congruent to B mod n. You are not able to differentiate between these two things. That's why you are having a problem. A mod n is not a relation. A mod n is an operation. You divide A by n, you get a remainder. You write the remainder in. This is similar to taking A square. A square is not a relation. It's some operation you do. It's a function. You can think of A mod n as something similar to that. If you have 4, 4 mod 2 is the residue you get when you divide, or the remainder you get when you divide 4 by 2. So 4 mod 2 is equal to 0. But if I write 4 mod 2 is congruent to 8 mod 2, what does it mean? This means that when I divide 4 by 2, I get the same remainder as when I divide 8 by 2. Right? The remainder I get when I divide 4 and 8 by 2 is the same. So 4 is related to 2. 4 and 8 are in a relation. So 4 and 8 belong to the same equivalence class. If the operation is congruent C modulo 2. if the relation is congruency modulo. Do you understand? Yeah, yeah. Uh, A mod n, yeah, 4 is congruent to 8 if 4 mod 2 is equal to 8 mod 2. Yeah. So we are using this mod 2 here to define this relation, congruent relation. But here we are simply using the mod 2 operation itself. So when I say Zn, this is the set of residues. I say Z3. This is the set of reminders I can get when I divide a number by, when I divide any integer by 3. And there are only three possibilities for that. I can either get the remainder 0 when I divide a multiple of 3 by 3. Or if I divide a multiple of 3 plus 1, then the remainder I get is 1. Or if I divide a multiple of 3 plus 2, I get the remainder 2. So Z3 is the set of the remainders that you get when you divide an integer by 3, right? But Z mod 3Z is the equivalence class of 0, 1 and 2. That is, this is the set of all elements that give you remainder 0 when you divide by 3. This is the set of all elements that give you remainder 1. This is the remainder itself. This is the set of all remainders that set of all elements that give you this remainder. That's the difference, right? There is a difference, right? See this notation I can't explain easily because that was the next that would have come up in later lectures in group theory. This is actually the um quotient group Z mod 3Z is a quotient group. Yes. Yeah, given a subgroup, you can given a subgroup G, you can get sorry, if you have a group, then you take a subgroup H, then you can get a set of equivalence classes. One would be H, another would be A plus H, another would be B plus H, etc. And this itself forms a group. With the definition A plus H plus B plus H, where A and B are group elements in G, is equal to A plus B plus H. And A plus H into B plus H is AB plus H. With this definition, the set of H, A plus H, B plus H, etc. will form a group. And suppose H is 0, 1, 2, 3. 4 plus H would be adding 4 to each of the elements in H. 4, 5, 6, 7. 3 plus H would be adding 3 to each of the elements in H. That is 3, 4, 5, 6, so on. So if, huh? Yes, it need not be a subgroup. But it will, since H is a subgroup and G is a group, and you're adding elements of this, there won't be any common elements here, right? These will always have distinct elements because why is that? That is because that let's say you had some H1 in H, capital H, and you had 4 plus H2 in this 4 plus H set, in this set. Then if you said 4 plus H2 is equal to H1, that would imply 4 is equal to H1 minus H2. But H1 is in capital H, H2 is in this capital H. So H1 minus H2 would have been in capital H. So 4 would have to be in capital H. So two different sets of this form will have distinct elements. They can't have same elements. And if you take the set of all such, but another thing is, um, you can't always say that this A plus H and B plus H are different. So either A plus, if B is an element of A plus H, if B initially you have H, then you add some element and you get A plus H. Suppose this element is A was in H, then A plus H would be the same as H itself. Yeah, because it's a subgroup. I mean, this of course is, I just took random elements. This is not a subgroup. I haven't told you what the group is, what the subgroup is. But if you took one subgroup element and added it to all the other subgroup elements, you would still get a subgroup element only, right? By closure. So that even though this 4 plus H is not a subgroup, that would still hold here. If you took 5 and added it to H, instead of here you got 4 plus H. If you took 5 and added it to H, you would get 5 plus H, which would be equal to this 4 plus H. Of course, it doesn't happen here because H is not actually a subgroup. I just written a random set. But if H was a subgroup, if you took any of the elements in this A plus H, that is 4 plus H, and added it to H, you would still get back 4 plus H. So 4 plus H would be equal to 5 plus H. This would be equal to 6 plus H. This would be equal to 7 plus H. If H was a subgroup. Then 8 plus H would be a different one. Since 8 does not belong to 4 plus H does not belong to H. 8 plus H would be a different set. Again, you would get 8, 9, 10, 11, something like this. So if you keep doing it with every group element, this 4, 8 are all group elements, elements from G. If you keep doing it, at the end you will cover all the elements in G. They will all belong to at least one of these sets. So this A plus H, B plus and all will form a partition of G. Is that clear? Yeah, once they form a partition, you remember in the preliminaries we said for every partition there is an equivalence relation and there will be equivalence classes. We defined if you given a partition, define the relation A is related to B if A and B belong to the same partition. same set in the partition. That is an equivalence relation. And the equivalence classes of that relation are simply the sets in the partition. You remember that? Yeah, so you can do that here since this will give you a partition. You can define the equivalence relation such that two of these elements are related if they belong to the same set in the partition. Then you'll have these all will become equivalence classes, right? HA plus B plus H, etc. So this set of equivalence classes will form a group with addition defined this way and multiplication defined this way. So here this Z is this G is Z mod 3Z, and 3Z is a subgroup. NZ is a subgroup for any n. So that Z mod NZ is simply 3Z is the set of all multiples of 3. But what are the it is the but it is also an equivalence class. And how do you write an equivalence class? You pick a representative in the set and use it to write the equivalence class, right? So 0 is a member of multiples of 3. So the equivalence class containing all multiples of 3 can be represented by 0. That's why this is related. Or you could have written it as 3z itself instead of 0 bar. Then this would have been 1 plus 3z. You add 1 to every element of 3z. Then what would you get? You get elements that are of the form multiple of 3 plus 1. What will they give you as the remainder if you divide by 3? They will give you 1. And this would be 2 plus 3z. If you had continued with groups, this would have been clearer. I'll see later if this gets more difficult, I'll do that. Yes, yes, all integers. Yes. 3 plus 3z is the same as 0 plus 3z. That's why. 4 plus 3z is the same as 1 plus 3z. Because what is 3z? It's set of all multiples of 3. So it is minus 6, minus 3, 0, 3, 6, etc. What is 3 plus 3z? 3 plus 3z, you add 3 to all the elements of 0. What is this? Yeah, this is minus 3, 0, 3, 6. It's the same thing, right? Yes, it will be isomorphic to Zn. You can get a direct bijection between Zn and Z mod Nz. Simply by mapping 0 to 0 bar, 1 to 1 bar, 2 to 2 bar. You map it like this, n minus 1 to n minus 1 bar. Yes. So what will happen if you multiply, let's say you have Z3 and Z mod 3Z with the mapping 0 goes to 0 bar, 1 goes to 1 bar and 2 goes to 2 bar. What will happen if you multiply 2 with 2 in Zn? 2 times 2 in Z3. What is 2 bar times 2 bar? We defined this to be 2 times 2 mod n. Yeah, so what is 2 times 2 mod 3? This one, right? This is 2 times 2 mod 3. Yeah, so it would be mapped to 1 bar. So even though they are actually containing different elements, here it's a set of numbers, here it's a set of equivalence classes. But the operations are defined in such a way that you can multiply multiplication in Zn and multiplication in Z mod n, they are identical. Yeah, then it would simply mean that all your coefficients belong to Z mod n Z. That's all. You would have 0, 2 bar x square plus 3 bar 1 bar x plus 0 bar. Since these are isomorphic, many times you simply write this also as 2x plus 0. Uh, it, no, no problem. See, when you're talking about straight lines, what is a straight line? Straight line is a set of points, collection of infinite number of points, right? But you can easily deal with straight lines. Two lines meet each other. There are two lines are parallel to each other. Every single time, do you think about the fact that they are a set of points? Or do you think them as simply lines? Yeah, you don't think about the fact that they are made up of points, right? Then when it comes to a triangle, do you think of it as three lines intersecting such that the interior angles are 180, or do you also think about the points consisting of it? Or do you care about the lines consisting of it? Or not always, right? Yeah. So similar to that, here the fact that equivalence class is made up of and is actually a set of points, it doesn't matter to us at all. We simply treat it as an element of the group Z mod 3Z. And then we define the addition and multiplication using the representative. So even though 0 bar is a set, we only deal with the representative 0. It's called quotienting. Yeah, you say Z mod NZ. No, not slash. You say Z mod NZ. And here also, if it's for G, you say G mod H for this, for arbitrary G and H. So here we had this G mod H. This was for groups, right? You can do that for rings also. You'll see that later. You can define this quotient group, the quotient ring instead of quotient group, where you can have R mod I, and then that will give you elements, and that will form a ring. So how this H, A plus H, B plus H all form the set of that formed a group. I, A plus I, etc. will form a ring. Then when this I has certain properties, that R mod I can become a field. Okay, I need to use the washroom. I'll be back in 5 minutes. All right. Are you there? Okay. Now, since we had a polynomial g of x in R of x, and we said pick an element alpha in the ring R. X minus alpha is a monic polynomial in R of x because the coefficient of x is 1, which is a member of R, and the constant coefficient a0 is equal to minus alpha, which is a member of R. Then we divided g of x by x minus alpha. By the division algorithm, we can write g of x is equal to x minus alpha times q of x. Q of x is the quotient polynomial plus r of x, where r of x is either the zero polynomial or it is a polynomial whose degree is less than the divisor. Here the divisor is x minus alpha whose degree is 1. Degree less than 1 means it's a degree 0 polynomial. So it's either a non-zero constant or it is 0, which just simply means r of x is a constant. Now g of x is x minus alpha into q of x plus r of x is actually this is an identically true statement. It is true for all values of x. If you substitute some value of x, it won't change. Now r of x is equal to a constant would mean that regardless of what x you give, you substitute in this expression, r of x will remain the same. So substitute alpha in place of x. What will you get? You will get g of alpha equals alpha minus alpha into q of alpha plus r of alpha. But alpha minus alpha is 0. So r of alpha is equal to g of alpha. But remember r of x is a constant. So whether you substitute alpha or some other value of x, it will have the same value. So r of x is g of alpha for all x. What does r of x is the remainder when you divide g of x by x minus alpha. So that means if you divide g of x by x minus alpha, the remainder is g of alpha. Now look at this example. Suppose my f of x was 2x plus 1 and g was x squared plus 1. Both are in z of x. You divide f by g by f to find the remainder. Okay, you can't actually do it in z of x, but we'll try q of x. Then you can multiply by half x to get x squared plus x by 2. To subtract, you'll get minus x by 2, bring down 1. Then you multiply by minus 1 by 4, you'll get minus x by 2 minus 1 by 4. And you again subtract, you'll get 5 by 4. Degree of 5 by 4 is 0, is less than the degree of 2x plus 1, so we stop. So the remainder, if you divide x square plus 1 by 2x plus 1 is 5 by 4. But you could have done this in a different way also. What did he say? I showed you something earlier, right? Suppose you have g of x is equal to you divide by f of x, you get f of x q of x plus r of x, where degree of r of x is less than degree of f of x. Then if you had instead divided by f of x by 2, right? You would have simply received the answer to be this if you had divided by f of x by 2. Because degree of f of x by 2 is also equal to degree of f. R of x has degree less than f of x means that R of x also has degree less than f of x by 2. So you would receive the same remainder twice the quotient. That's all. So the remainder doesn't change if you multiply the divisor by some number, or if you divide it by some number. Yes, yes, yes. That should be true. It should, yeah. That's why 2 must be a unit of the ring. Then this instead of dividing by 2, you can multiply the inverse by 2 inverse. Then since 2 is a unit, 2 inverse will be some element of the ring itself. Yeah. So here what you can do, but the point is that if it is a unit, you can do this and then the remainder won't change. So using this type of manipulation, what you can do is you can write this 2x plus 1 as in q of x, you can write it as 2 into x plus half. And half belongs to rational numbers, q. So you can do this. Now, what do you do? Now, what is the remainder if you divide x squared plus 1 by 2x plus 1? It's the same as if you divide x squared plus 1 by 2 into x plus half. Or if you divide it by x plus half. Whether you divide by x plus half or 2 into x plus half, you'll get the same remainder. So instead of dividing it, if all you care about is the remainder, instead of dividing by 2 into x plus half, which is 2x plus 1, you divide by only x plus half. But x plus half can be written as x minus half. So in this theorem, alpha is minus half, which is a member of Q. So the remainder will be g of alpha. Here g of x is x square plus 1. So the remainder is 1 minute. I have to charge my tablet. The remainder is g of alpha, where alpha is minus half and g is x square plus 1. So it is minus half square plus 1, 5 by 4. We can directly write it. Another use is, suppose you want to find out if um, suppose g of x belongs to R of x. If you want to find out, if you want to find out if x divides g of x, and if x divides g of x, that is, when you divide by x, you must get 0 as the remainder. But x is also equal to x minus 0. So alpha is 0. The remainder, when you divide g of x by x minus 0, is g of 0. But if x divides g of x, that remainder must be equal to 0. So if you want to find out x divides g of x if g of 0 is equal to 0. That's one way to find out if x is a factor of g of x. Similarly, if you want to find out uh, if x minus 1 divides g of x, then g of 1 must be equal to 0. So if you want to find whether x minus alpha is a factor, the remainder by substituting alpha must be equal to 0. That's one way of finding out simple factors of polynomial. And that will be useful later when we want to find out if a polynomial is an irreducible polynomial or not. Yeah, it does not have any factor other than one and multiples of itself. So in integers, um, yeah, you have prime numbers, so the factors are one and the prime number itself. But here, since these are polynomials, um, the if you multiply by a unit, then we don't differentiate it between those two polynomials. So that will also be a factor, but we don't consider it as a separate factor. So what I mean to say is this 2x plus n and 2 into x plus half. We don't consider them as separate polynomials and say that x plus half is a factor of 2x plus 1 because they differ only by a unit. X plus half is a factor of 2x plus 1, right? You can write 2x plus 1 as 2 into x plus half, right? But yeah, so the only factors for an irreducible polynomial will be either 1 or um factors such that they differ by a unit. Whereas in integer case, only the other than 1, only the prime number itself is its factor. So there are like small differences like that. Similar to how in the division algorithm, instead of r of x being between 0 and the divisor, here r of x is either 0 or the degree of r of x is between 0 and the degree of divisor. Similar to this, you can actually define polynomials of multiple variables. So you can define r of x1, x2, xn to be a polynomial in which each term has some power of x1, some power of x2, some power of xn. Maybe this power is 0 so that it doesn't appear. But the coefficient is from r. So addition will be defined in the same way. That is 2x1, x2 plus 3x1. We add it with 5x1, x2 plus 6x2. You will get 7x1, x2 plus 3x1 plus 6x2. These are in R of x1, x2. So you can have any of the x1, x2 up to xn in the, and also you can have powers of this also. You can have 2x1 square x2 like this. Multiplication is also carried out in a similar fashion. So this will also be a ring. So one way to understand this type of ring is, first you have R is a ring, right? Huh? If R is a ring, then R of x is a ring, right? Then R of x, y is also a ring, right? Yeah, because R of x is a ring. If you simply, instead of, you forget this, you call this some h, some ring h. Then you will, this will be simply h of y, where the coefficients come from h. But actually h itself is a ring with polynomials in x. So the coefficients are polynomials in x. Then if h of y, you can call this some other uh, k. That is also a ring, because h is a ring, h of y is a ring. Then you can add k of z, polynomials in z. But the coefficients are from k, where k is polynomials in y with coefficients in h, where h itself is polynomials in x with coefficients in r. So at the end of the day, this will actually be with coefficients in r and with three variables x, y, z. So you can keep chaining it in this way, as many variables as you want, but finite number of variables. You can't have infinite number of variables. So that is also a ring. So these are polynomial rings, which are one of the most important rings for our study, especially for fields. Finite fields are, there are two types, like infinite fields, polynomial rings are not so important, but finite fields, polynomial rings are the basis. They are on which we build the finite fields. They're the building blocks. Like how you do arithmetic using numbers. Numbers are the important aspect, right? Integers. Then from integers you can get rational numbers, and from rational numbers you can get real numbers, right? Like that, from polynomial rings you can get all finite fields. Yes, directly no, but using it we can construct. Yeah, using polynomials you can construct fields, polynomial things. Yes, I'll do that. I'll do that. I'll do one lecture on finite fields. Okay, this is the introduction, basic introduction to rings. Tomorrow I will do homomorphisms in rings. We saw homomorphisms in groups. Homomorphism in rings have additional one property. It's additional properties. And unlike homomorphism in groups, for many cases the homomorphism in ring is very restricted. We'll do examples of that. Then we'll look at the kernels of these homomorphisms, like the kernel of homomorphism of proofs. There, what happened was the kernel was the sub. Every kernel of a homomorphism was a subgroup of the domain of the homomorphism. Here, what will happen is every kernel of a ring homomorphism is an ideal of the domain ring, and from there we'll define the concept of ideal. Yeah. No, from this week we'll have on Saturday, Sunday only. Uh, is that okay? Yeah. No, no, not tomorrow. Next class, Saturday. Yeah. So this week and next week on Saturday, Sunday we'll have classes. So four more classes we'll have. Yeah. I'll cover ideals in one lecture and finite fields in one lecture. Other topics, uh, as much as we can, we'll cover in two of the lectures. So we'll see. And five fields, I'll mostly do finite fields and the very basic finite fields. Okay. Good night. Bye.